Hello everyone, I'm Yuan Feng from University of Technology, Sydney. Today, I'm very pleased to have this opportunity to report our work on the verification of nondeterministic quantum programs. This is a joint work with my PhD student Yingte at UTS. Introducing nondeterminism into a programming language allows one to describe a specification and its possible implementations in the same language. From a verification perspective, it provides a way to reason about the correctness of an abstract specification before it is fully implemented, making it possible to detect bugs at the earliest stage of software development. Nondeterminism was first introduced into quantum programming in 2004 by Giuliani. Termination analysis of nondeterministic quantum programs was studied in the 2014 paper, where a quantum program is represented as a set of deterministic quantum Markov chains. Later on, termination analysis was extended to a quantum programming language, which involves both demonic and organic nondeterminism. In contrast, the contribution of our paper is the verification of a wider range of properties of quantum programs beyond termination. To see how nondeterminism can be useful in describing quantum systems, let's look at a simple example. This is the circuit of quantum error correction scheme which corrects a bit flip error on any of the 3 qubits. You can see from the blue part that the uncontrollable noise can be represented as a nondeterministic choice of the environment. We have a nondeterministic choice among 4 possibilities, corresponding to the cases of no error, error on the first, second, and the third qubit, respectively. Furthermore, nondeterminism can be used to represent the different implementations of an oracle in a quantum algorithm. For example, in Deutsch algorithm, we need to decide whether a given oracle implements a constant Boolean function, meaning that f0 equals f1, or a balanced one, meaning that f0 and f1 are different. Note that in each case, the implementation of f is not unique. Again, you can see from the blue part that this non-uniqueness can also be represented as a nondeterministic choice. The purpose of our paper is to provide a technique to verify the correctness of nondeterministic quantum programs. The procedure consists of 3 parts: a program with nondeterministic choices to describe the behavior of the system, a correctness formula to encode the desired property, and using horologic system for formal verification. In the following, we will elaborate on these 3 parts in turn. First, let's introduce the target language. We extend the purely quantum wire language defined in the literature to describe quantum programs with nondeterministic choices. Specifically, we introduce the box construct to denote nondeterministic choice between 2 programs. This slide shows the denotational semantics of programs written in this language. For each quantum program, the semantics is given as a set of suboperators on the associated Hilbert space. Our definition follows the lifted model instead of the more popular relational model in probabilistic programming theory. In fact, as we show in our paper, extending the relational model to nondeterministic quantum programs is problematic, as it would distinguish certain programs which are indistinguishable by any physical means. Now we have defined the syntax and semantics of our target language. The next step is how to describe the properties we are concerned with. As in classical Hoare logic, we define correctness formulas or Hoare triples for this purpose. Recall that for deterministic quantum programs, we take Hermitian operators between 0 and identity as quantum predicates. For a predicate M and a quantum state ρ, trace M ρ is the expected outcome when measuring observable M on ρ. In the context of verification, it is interpreted as the degree of ρ satisfying property M. Note also that this is the natural extension of predicates for probabilistic programs. However, although the set of Hermitian operators between 0 and identity is a complete partial order set, it does not form a lattice. Therefore, it is not expressive enough for the verification of nondeterministic quantum programs. To deal with this problem, we take subsets of Hermitian operators as quantum assertions. Under this definition, the expectation of a quantum state ρ satisfying an assertion theta is then defined as the minimum value of ρ satisfying all the quantum predicate M in theta. This reflects a pessimistic view of nondeterminism. It provides a guaranteed expected satisfaction in the presence of possibly demonic nondeterminism. The property of a quantum program is then expressed by a correctness formula or Hoare triple with this form. Here S is a quantum program, and theta and psi are quantum assertions, called precondition and postcondition of S respectively. Using the definitions above, we can then define the notions of total and partial correctness. Intuitively, in total correctness, the precondition serves as a lower bound on the expected value of the output states satisfying the postcondition. In partial correctness, the non-termination probability is also considered. Again, these definitions are natural extension of those for deterministic quantum programs. We have finished the definition of the first two parts, the target language and the correctness properties we are concerned with. Now let's look at the final step, the Hoare logic system. This is the logic system we proposed for partial correctness of non-deterministic quantum programs. It is similar to the one for deterministic quantum programs, which in turn is motivated by the classical Hoare logic. Most of the rules are intuitive and easy to understand. In particular, for while loops, we use a loop invariant to help reasoning. We also introduce a new proof rule, Union, to combine several smaller proofs to become a larger one. A proof system for total correctness can be similarly defined. The only difference is that we need to introduce a similar notion of ranking function, called ranking assertions, to guarantee termination of while loops. Interestingly, we can show that our proof systems are both sound and relatively complete with respect to the total or partial correctness. In other words, a correctness formula is partially correct if and only if it can be proven to be true in the proof system for partial correctness. Similar result can be shown for total correctness. This slide shows the verification procedure applied to the example of bit flip quantum error correction. We have already seen how this error correction scheme can be described with the non-deterministic quantum program. In the correctness formula, the state alpha 0 cat 0 plus alpha 1 cat 1 appearing in both the precondition and the postcondition is an arbitrary one, meaning that the error correction scheme keeps any input state unchanged, or any possible error corrected. The proof outline generated by our proof system is shown on the far right. In general, carrying out formal verification is tedious and involves a large number of matrix manipulations. To ease the burden on human users, we implement a prototype proof assistant NQPV to automate routine parts of the verification process. It is a standalone Python project. It takes as input a correctness formula and loop invariants, and check if the formula is true according to partial correctness. To further simplify usage, NQPV also allows users to omit preconditions and specify only postconditions. In this case, the tool outputs the weakest precondition it can compute using the given postcondition and user-supplied loop invariants. This slide shows the input and output of our tool for the verification of a non-deterministic quantum walk. The matrices var0, var1, and var2 are generated by our tool to represent predicates used in the proof outline. The detailed information of these operators can be shown using the show command. Finally, this tool has been open sourced on GitHub and uploaded to PyPI as a package. You're welcome to have a try.